So I'll start again with the two formation scenario. I was telling you that there are two phases. The first phase that is very quick and it occurs very early on in time. Let's say from the Big Bang to 3 billion year, Redshift, let's say 2, but it's really work in progress. A very quick star formation episode, a starburst that quickly quenched, form what we call a red nugget. This is a very compact but yet massive object. We're talking about less than 2 kiloparsec on the sky and masses that can reach up to 10 to the 11 solar masses. Those red nuggets are on average 4 to 6 times more compact than local galaxies, and they are as massive as early type galaxies. Then the second phase starts normally, and it's characterized by mergers, interactions, gas inflows. So an accreted population falls into this in situ core and increases the size by a factor of 4 to 6 and forms what we today call local giant ETGs, elliptical galaxies. Those galaxies have a typical size that can reach up to 10 kiloparsec or even more sometimes in some extreme cases, and they are only slightly more massive than the red nuggets. So what has been proposed is that the red nuggets are indeed the innermost in situ core of today local giant ETGs. Nevertheless, merging is a stochastic phenomenon. And therefore, it's predicted that a small fraction of red nuggets do not undergo the second phase, so do not experience any merger and interactions, and they evolve undisturbed passively from the first phase of the formation until today. And this is what we call relic galaxies. And as you can understand, those are very ultra-compact, massive objects because they didn't increase their size due to the merger and interactions. And they are very, very important objects, local laboratories, to study the first phase of the formation scenario in the universe. Because in local giant ETGs, the two populations are mixed up together, and it's not very easy to disentangle between what often is called in situ and accreted population. So if we can find relics and characterize their stellar population, we can basically have a relic of the ancient universe. So this scenario is also supported by two lines of observations. On one side, the size evolution of early type galaxies. Here I'm plotting as an example a plot by Van der Wel et al. In 2014, where you can see different mass bins, galaxies binned in mass. So the different lines from top to bottom are in decreasing order of stellar masses. And x-axis is the redshift. So from redshift 3 to today, there's a clear increment in the size in the effective radii of the galaxies for all the bins except for the lowest one. So basically, passive, massive galaxies, those are only early type galaxies, are increasing their size in the second formation scenario, in the second phase of the formation scenario. The other piece of evidence came in 2017. On the right side of the slides, you can see a plot from Ferre Matteo et al., which is reporting the discovery of 3 local relics. Those are 3 galaxies with redshift 0.002. And one of them, NGC 1277, was already studied by Trujillo in previous papers. And this is the most relic object in the local universe, with the radius, effective radius of 1.2 kiloparsec. The other 2 galaxies are also local, also very massive, and also very compact. However, if you see, if you see the rightmost plot, you can see there it seems to exist a sort of degree of relicness. This is the percentage of mass that has been assembled from the Big Bang. And if you can see the yellow system, which is 1277, the top panel, this galaxy assembled more than 90% of its mass 1 gigayears after the Big Bang. Whereas the greenish system, MRK 1216, it took a little bit longer, and it looks like it had two different steps of mass assembly, but nevertheless, after only 1 gigayears from the Big Bang, those galaxies were completely, the stars in these galaxies were completely in place, and they were so compact as you can see the radius, the radii in the images. So 2 kiloparsec, 2.3 kiloparsec is the bigger one. In order to confirm actually that this is that a relic, a degree of relics really exists, we need to discover more of those systems. So another important point is what makes relics interesting. Again, from Ferre Matteo papers, we can see that they have the stars have a dwarf rich or bottom heavy stellar initial mass function. This means that those objects have a larger population of stars below masses, solar masses 0.5. So stars with masses below 0.5 solar. It's true where several effective radii. Ferre Matteo et al. Had high spatial resolution spectroscopy for those objects, and she can prove until 5 effective radii. But here, in order to compare to normal size ATGs, I'm plotting the IMF profiles as function of radius up to 1 effective radii only. And if you can see, the IMF slope stays almost constant for the 3 relics, which are the colored lines, but it decreases with radius. For example, of normal size ATGs. This is a collection of ATGs that I got from Francesco La Barbera, its shooter data, myself, Muse data, and other Grantecan data from Martin Navarro, 2017, if I'm not wrong. Anyway, you can see that for normal size ATGs, the population of stars described by a dwarf-rich stellar mass function is restricted in the very central region, whereas for relics, this is true at all radii. Another very interesting fact about relics, about these 3 relics, is that they host a uber-massive black hole. They scatter outside the bulge mass, black hole mass relation for normal sized galaxies that you can find on the right upper panel. Here, grayish points are normal sized galaxies, and the black and blue lines is the relation, the local stellar mass bulge, black hole mass bulge mass relation. And the black bigger point and triangles are the galaxies, the confirmed or the candidate to be relics. And as you can see, the black hole mass is always above the relation. And on the bottom panel, you can see a picture of a possible scenario to explain this. This was also Ferre Matteo 2017. And basically what happened is that during the phase 1, during the first phase of the formation, the galaxy's core and the supermassive black holes are already in place. They assembled almost completely, and therefore the evolution, the subsequent evolution in the phase 2 only increases the galaxy mass, although not as much as size, as we discussed previously, but it does not change that much the super black hole mass, and therefore it moves the galaxy horizontally on this plot, and it brings it back to the black hole mass bulge mass relation for local giant elliptical. This is only a scenario, and I stress again that in order to draw conclusions, we should find more of those galaxies, and hopefully also extending a little bit the redshift range in order, in a sense, to bridge the gap between high redshift red nuggets that are observed and studied, but not with the same amount of particular than these 3 local objects. And this is why, as Crescenzo anticipated, we started the KIDS collaboration that I'm going to describe you in a second. Another important point is that we don't know a priori how many relics we should expect today and in the redshift window that goes from 0 to 0.5, again, in this aim of bridging the gap. This is a plot that we made several times in several different versions. This is the up-to-date latest version that's going to be in the paper in preparation, the first INSPIRE paper I'm going to describe you in a while. And this is collecting all the observations and simulations that constrain the number density as a function of redshift in these windows for ultra-compact massive galaxies. Please pay attention to the fact that those are not necessarily relics. Those are ultra-compact massive galaxies, young and old. So we're still not there yet. We still do not have the characterization of the stellar population in this plot. What you can see from this plot is that there is a huge disagreement between on the number density of objects, especially in the lowest redshift window, between the two between different observational results. For instance, Poggianti et al., the red triangle, and Sauder or Taylor et al., they predict almost 3 order of magnitudes different results. And by the way, the bright triangle at redshift 0, this is the Ferret-Mateu et al. Result from the 3 local relics, whereas black squares are the results that we obtain with the kids within the kids collaboration in Tortora 2018 and Scognamiglio 2020. Also in this same plot, I'm plotting the results from some simulations. For instance, the brownish dotted line is from the Lustris simulation, Vellons et al. 2016. And this is considering counting the galaxies that didn't change. They changed the stellar mass by less than 10% by the moment they form. So they form, and through the evolution, the passive evolution, the undisturbed evolution, if you want, they only change by 10% their stellar mass. So from the point of view of simulations, you have that between 1 and 15% of the galaxies can survive untouched. Again, considering this 10% of the mass, we get this line until today. But indeed, this number heavily depends on the ingredients, the assumptions, and above all, on the physical mechanisms that are acting during the second phase. For instance, the relative contribution between major and minor mergers displays a very high role, a very heavy role in this game, but also how many mergers do the galaxy experience through their cosmic evolution. So basically, the take-home message is that by finding and characterizing, by counting, finding and characterizing relics across cosmic time, we can study possible physical scenarios driving the formation and size evolution of galaxies in the context of the two-phase formation. So basically, I convinced you that those are valuable systems. Now I have to show you briefly how we find them. And this is what has been already introduced by Crescenzo, a project that he started as PI with a series of INAF collaborators that are listed there below, and other people that I'm not listing just because this is an INAF talk, but it's a long list of collaborators belonging to the KIDS team, and it's towards a census of supercompact massive galaxies in the KIDS survey. So how do we find relics? First, we need to select ultra-compact galaxies, and this is a collection of what people have been done with different selection criteria and thresholds, but actually it's always the same principle. You plot stellar masses versus radii, and you select massive and small objects. Sometimes the threshold in radii vary a little bit between 1.5 and 2 kiloparsec, and also the threshold in stellar mass can vary between 5 times 10 to the 10 and 8 times 10 to the 10 solar masses, but nevertheless, those are massive and quiescent, very small systems. Obviously, because they are very small, we have to make sure that they are not point-like, they are extended, although a little bit. And within the KIDS collaboration, we do it through colors. We are lucky enough to have optical and infrared colors with KIDS plus Viking. And here in this particular plot, I'm showing the G minus J versus J minus K, or the other way around, actually. There is a very valuable plot to separate stars from QSOs and from galaxies. And here the red squared points are indeed our candidates, and the majority of them are in this yellow region, which is where galaxies, so extended extragalactic objects, are. After selecting them, we have to study the structure parameters, and we do that thanks to very high resolution, spatial resolution KIDS images. In particular, we are working with G, R, and I bands, and we are considering always the R band as, let's say, reference band, because this is the one with the highest resolution image. Here I'm showing you a series of plots from Tortora 2016 and Tortora 2018. In particular, in the upper row, I want to point the attention. This is a series of plots showing the characteristics of these systems, morphological and photometric characteristics. But what I want to point the attention to is the fact that we a priori used photometric redshifts to estimate the effective radii and the stellar masses. So as I was describing, I'll try to be quicker. By changing the redshift from photometric to spectroscopic, we are slightly changing, because those two numbers are not necessarily identical, we're also changing the estimates on effective radii and masses. And therefore, it is important to obtain spectroscopy to confirm the massive and compact nature of these objects. And this is what we do in a follow-up project. Crescenzo, can you move one slide forward? Where we obtain a low-resolution spectroscopy on a sample of roughly 50 to 70 objects. And you can see the spectra on the left bottom panel. And indeed, this is a nice confirmation that the spectra are those characteristics of massive and passive objects. You can see the 4,000 break, for instance, that is a clear indicator of old population. I'm also showing two random fits here on the top left. And on the top right, you can find a redshift versus color plot where all the points, doesn't matter which colors, are the candidates for which we have spectroscopy. And therefore, we have a confirmation of the massive and passiveness. On top of those, I'm plotting a Bruce and Charlotte simple stellar population models with 12 gigayears in black and 8 gigayears in blue. The age of the universe between redshift 0.1 and 0.5 ranges between, let's say, 11 and 8, 9 gigayears, and therefore I'm using these ages in the stellar population models to select candidates to be relic. And actually, those are the green points in this plot, whereas we sort of discarded because those seem to be a bit younger in terms of ages. And basically, the last step, what is missing, is to constrain the stellar population in great details for these green objects that have been selected to be relic candidates, and identify those with stars as old as the universe, and possibly in alpha over iron, because alpha over iron, it's some sort of a time clock for star formation episodes. The higher the alpha over iron abundance is, the quicker the star formation episode was. So if Crescenzo is so kind to go to the next slide, I'm finally introducing to you the INSPIRE project, the Investigate Stellar Population in Relics. This is a project that we started in 2019, and I was the PI of ESO large program, which was awarded in period 104, to observe a sample of those objects with 145 hours within 2 periods, so within 1 year, with the X-shooter BLT spectrograph. The current status, the project is ongoing. We obtained already 42 hours and we completed 11 systems. 17 are already partially observed. And the important thing, Crescenzo, can you move to the next slide? The important thing is that we are we are covering a broad range of Ryan deck, and therefore the systems are observable all over the year. We are covering a big enough window in redshift in order to say something about the relic number density in the same redshift windows as simulation and other papers. And we're also covering a broad range of magnitudes, although we stay bright in a sense, in order to have manageable observation times. As you know, because of the coronavirus, the observatory, the ESO observatory, is currently shut down, so we do not receive any data for the moment, but the project is in carryover for period 104, and it will be in carryover for period 105 as soon as we know something about the future of the observatory. So we will get all the 154 hours that we have been awarded. And now, in the few minutes that I'm left, if Crescenzo moves the slide, I can present to you the pilot program on which we're working already, and the paper will be published, will be submitted in maximum a month, I hope. And in this pilot program, we are focusing on 3 systems. Those are plotted here in R-band, one Arch-minute image, very representative of the whole sample, because actually we are lucky enough to have the most compact objects. This is the middle panel with an effective radii of 0.65 kiloparsec, which is roughly 0.15 arc seconds on sky. So 1 pixel in shooter. Then we have the most massive one on the left and the closest in Redshift one on the right. To be able to prove the strategy also for observing time, because those systems have different number of OBs. And if Crescenzo moves one further, I can show you the final spectra. This is a collection of respectively 2, 3, and 4 OBs, UVB plus visual. I don't know if you know that X-Shooter is able to observe in one shot from the UVB to the near infrared. For the moment, I'm combining the UVB and VIS arm because they have the same spectral binning. And I'm doing that by correcting the resolution of the final spectrum in order to have the same resolution across lambda. And here you can see that the data reduction is still not perfect. There are spikes and bad sky subtracted. The gray region is the place where I join together UVB and VIS, whereas the purple region is the big telluric line that we didn't clean yet. And I'm fitting kinematics and stellar population within the white region. And you can see some lines highlighted as vertical red lines. If Crescenzo moves on, I can show you the infrared, which is not ready to be used yet because we have to correct for telluric lines that in the infrared are terrible. And obviously the infrared is going to play a crucial role in constraining the initial mass function, because dwarf stars are emitting much stronger in the infrared. The cold dwarf population emits by 30% of the, roughly 30% of the lights in the infrared, but only less than 5% in the optical. Nevertheless, the signal to noise from UVB and VIS is good enough to have some precise estimate of age, metallicity, and alpha over iron. You can see the first result in the next slide, where I am, where I am showing the PPXF, penalized pixel fitting routine by Capellari et al. Of the first most massive objects in our sample. This is performed with simple stellar population models from Miles that I interpolated in order to be able to change at the same time age, metallicity, and also alpha over iron. The velocity dispersion inferred from this spectrum, which is extracted from 3 pixels, so roughly 1 effective radii, a little bit more than 1 effective radius for this galaxy. It's the velocity dispersion is 250 kilometers per second, and this is sort of confirming the very massive nature of these objects. And results are confirming 100% that this is a relic. So it has an age of roughly 10.7 plus minus 1, with the age of the universe being 9.5, supersolar metallicity, and supersolar alpha over iron. I also wanted to point out that 2 people did the analysis with the same tool, but in a completely blind way. So I run PPXF on my computer. Giuseppe Dago in Santiago del Chile ran his PPXF on his computer with different parameters, but nevertheless we obtained something very consistent in terms of kinematics and stellar population. So I can 100% tell that we really confirm the first relic galaxies in the redshift windows at redshift 0.35. If Crescendo moves on, I'm happy to report that we're almost confirming also the second object. This is the lowest redshift object in our sample. The age of the universe at this redshift, the redshift is 0.17, and the age of the universe is roughly 11.5. And we have a stellar population with age of 10.8 plus minus 1, so perfectly consistent. Once again, supersolar metallicity. However, this time the alpha over iron seems to be roughly solar, and this might indicate that the star formation event was a little bit more extended in time with respect to the previous one. Nevertheless, the velocity dispersion is high, 240 plus minus 8 kilometers per second, and the radius for this galaxy is very small. So I would say that this is most likely another relic, perhaps with a degree of relics roughly lower than the previous one. Once again, we agree on stellar population and kinematics result from the blind analysis. Next slide. This is the third case, which is still work in progress. As you can see, this is the most compact galaxy that we have. And there are two things to note. The first one is that the velocity dispersion is below 200 kilometers per second. And this is in disagreement with the estimate we obtained from low signal to noise spectra. However, this means nothing because the spectrum we used before was really, really bad in terms of signal to noise. So I would tend to trust more this estimate. And for the velocity dispersion and rotation velocity, Pepe and I agree on the results. The problem we have comes with the stellar population because I do detect some gas in this galaxy. And if you see the residual, the purple magenta line shows some emission lines that comes from gas, most likely oxygen and some Balmer line. And as soon as I put the gas as additional component for the fitting, the stellar kinematics, the stellar population changes. Whereas for Pepe, this is not true. So Pepe obtains something more older and more metal richer than what I get. So I would say that for this particular system, we are still investigating and we are comparing the methods and the parameters. I don't want to go technical, but I do not feel confirm this galaxy as relic yet. Next slide, which is basically my conclusion. That's all.